Hi. Welcome back to my FOC class. This lecture is the continuation of Chapter 3 that we have learned in the previous video. In the previous video, we have learned the instructions to manipulate data, such as moving data between registers, from register to memory, and from memory to register using some of the addressing modes. In this video, you will be introduced to the arithmetic and logic instructions. These instructions are very important in computer, where it is used for calculations and logic. Arithmetic operations are probably one of the most common types of instructions we will use. Especially if the software being written involves manipulating large amounts of data, such as an incoming audio signal, graphics algorithms, speech processing algorithms, digital controllers, and audio processing. All involve a great deal of arithmetic work, so it's important to understand the types of data that we have, and how to perform the operation needed in the shortest amount of time and space. Recall from Chapter 2, that the program status register holds the current state of the machine or computer, which are, the flags, the mode, the interrupt bits, and the thumb bit for the processor core. There are 4 bits, N, Z, C, and V, in the uppermost nibble that help determine whether or not an instruction will be conditionally executed. There are several things that will set or clear the flags, as follows. Number 1. Instructions that are specifically used for setting and clearing flags, such as instruction TST or CMP. Number 2. Instructions that are told to set the flags by appending an S to the mnemonic. For example, MOVS would perform an MOV operation and set the flags afterward, since the S bit is set in the instruction. We can do this with all of the ALU instructions, so we control whether or not to update the flags. Number 3. A direct write to the program status register, where you explicitly set or clear flags. Now, let's look at the first arithmetic instruction. The add instruction. The operation is 32-bit. Format 1, where we have 2 operands, RD is the destination operand, while OP2 is the source operand. RD must be a register, while OP2 can be any general-purpose registers or an 8-bit immediate value. For the format 2, there are 3 operands, where RD is the destination operand, RM and OP2 are source operands. RD and RM are registers, while OP2 can be a register or an 8-bit immediate value. Please note that the add instruction without suffix s will not update the status flags. Now, let's look at the first example for add instruction. This instruction uses format 1, where we have only 2 operands. R0 is the destination and R1 is the source operand. For this instruction, the content of R1 will be added with the content of R0, and the result will be saved in R0. Assume that, initially R0 contains hex 4 and R1 contains hex 2. Therefore, after the microprocessor execute the instruction, we will have hex 6, which is 4 plus 2 in R0. This is another add example, where the source operand is now an 8-bit immediate value. Assume that initially, R0 contains hex 4, and R1 contains hex 2. After the microprocessor executes the instruction, the content of R0 is now updated to hex 104, which is 100 plus 4. The arithmetic instructions will affect the status flags after it is executed. Now, we will see how these instructions will affect the flags. In this example, we will determine the flag's condition after the add instruction is executed. Let's assume that the initial content of R0 and R1 are hex 7, FFF, FF, FF, and hex 1, respectively. Given the instruction as add R2, R0, R1, where the contents of R0 is added with the content of R1, and the result will be stored in R2. After the add, R2 will have hex 80 millions. And the value of flags are as follows. N equals to 1, Z equals to 0, C equals to 0, and V equals to 1. How to determine these flags? The easiest way is to do the calculation in binary number. Let's do this. First we convert hex 7, FFF, FF, FF into its binary representation like this. Then, we add with hex 132-bit. The result is this. Equivalent to hex 80 millions. Because the most significant bit is 1, indicates that this is negative 32-bit number. Therefore, n equals to 1. And the result is not equal to 0, hence, z must be equal to 0. There is also no carry is produced from bit 31 to bit 32. Therefore, c equal to 0. And the last one, overflow. To check for overflow, we need to know the range of a signed 32-bit number, where the minimum number is -2,147,483,648, and the maximum number is +2,147,483,647. Because the result is hex 80 millions, which equivalent to positive 2,147,483,648. Clearly, hex 80 millions is out of range for the 32-bit signed number. Therefore, V equal to 1 in this case. The instruction for subtract. The sub instruction. This instruction subtract a 32-bit number from a 32-bit number in destination register. There are two formats as well, just like in the add instruction. In this instruction, for example in format 1, RD subtract OP2, then the result is kept in RD, the destination operand. While for format 2, RM subtract OP2, and the result will be in RD. Again, the sub instruction, without the s suffix, will not update the status flags. Let's look at this example for sub instruction, using format 1. The instruction is sub, R0, R1, means R0 minus R1, and the result is stored in R0. Assume that R0 and R1 initially contain hex 4 and hex 2, respectively. Then, after the microprocessor execute the instruction, we will have hex 2 in R0, which is 4-2, and the content of R1 remain unchanged. And the condition flags are as follows. Now, let's verify how we get these values. In computer, a negative number is represented in 2's complement number. Therefore, 4 minus 2 is actually 4 plus negative 2. Now, let's look in binary representation. This is 4 in binary representation. And this is negative 2. This subtract is actually an add operation, because a subtractor circuit is built from an adder. The result from the operation is this. Let's see the condition flags, one by one. Look at the most significant bit, 0, means n equals to 0, indicates the result is positive. There is carry from bit 31 to bit 32, hence, c equals to 1. And because the result is hex 2, therefore, z equals to 0. And finally, V is equal to 0, because the result, hex 2 is definitely in the 32-bit range for sign number. The next arithmetic instruction is multiplication. There are three types of multiplication instruction. The first one is MUL, the second one is SMULL, and the third one is UMULL. For the MUL, the maximum result is 32-bit, and can have 2 or 3 operand. Observe that all the operands are general-purpose register, this means, immediate value is not allowed. For the SMULL, the sign multiply, where the result can be up to 64-bit. To do this, we need 2 general-purpose registers to store the result. The lower 32-bit result will be stored in RDLO, and the higher 32-bit result will be stored in RDHI. The last multiplication instruction is the UMULL, where the operation is similar to SMULL, but for unsigned number. Therefore, the result is 64-bit as well. This is an example of SMULL instruction, where we want to multiply the content of R2 to the content of R3. The result is 64-bit, stored in R0, and R1. After the microprocessor executes the instruction, this is the results in R0 and R1 respectively. This is how the result is generated. We want to multiply hex 7, FFF, FF, FF, with hex 100. And the result is 7FF, FF, FF, F00. We can see that the lower 32-bit, which is FF, 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 00, will be stored in R0, the RDLO, and the higher 32-bit, which is 00, 00, 00, 7F, will be stored in R1, the RDHI. Now, we will look at divide instruction. There are 2 types, which are SDIV for signed division, and UDIV for unsigned division. The operation is that, Rn will divide by Rm, and the result is stored in destination operand, Rd. Let's look at this SDIV instruction. SDIV, R0, R1, means the content of R0 is divided by the content of R1, and the result will be in R0. Assume that R0 initially contains this hex value, which equivalent to -10. And R1 initially contains hex 2. After the microprocessor execute the instruction, we will get this in R0, which is equivalent to -5. -10 divide by 2, the result is -5. This is the example for UDIV, divide unsigned. Let's the instruction be divide unsigned, R0, R1, where the content of R0 is divided by the content of R1, and the result will be stored in R0. If the initial values of R0 and R1 are 32-bit hex A and hex 2, respectively. After the instruction is executed, we will have 32-bit hex 5 in R0. After the arithmetic instructions, which are add, sub, multiply, and divide. Now, let's look at logic instructions for ARM microprocessor. These are the logic instructions. The AND, ORR, and EOR instructions perform bitwise, and OR, and exclusive OR, operations respectively on the values in RM and OP2, where OP2 can be a register or an immediate value. The BIC instruction performs an AND operation on the bits in RM with the complements of the corresponding bits in the value of OP2. The ORN instruction performs an OR operation on the bits in RM with the complements of the corresponding bits in the value of OP2. This example illustrates the AND, or an AND, instruction. Given the instruction as AND, R0, R1, R2, means the content of R1 is AND with the content of R2, and save the result in R0. Let's R0, R1, and R2 initially contain 0, hex 1, 2, 3, 4, and hex F, F, 0, 0, respectively. After the microprocessor executes the instruction, the content of R0 will be hex 1, 2, 0, 0, according to the AND logic operation. This is how we get hex 1, 2, 0, 0 in R0. We have hex 1, 2, 3, 4 in R1. And hex F, F, 0, 0 in R2. Then the AND operation will result in hex 1, 2, 0, 0 in R0. Then for the BIC instruction, where the instruction is BIC, R0, R1, R2. So, we need to get the complement number of the number in R2 first before we can perform the AND operation with the content of R1. If the contents of R0, R1, and R2 are the same with the previous example, then after the instruction is executed, the content of R0 is now updated to hex 3, 4. This is how it is performed. First, we get the ones complement of the content of R2. Here is the complement value. Then we perform the AND operation with the content of R1. Therefore, the result is hex 3, 4 in R0. We are now go to another group of instructions, which are the shift and rotate instructions. There are 5 instructions as follows. Number 1. ASR. Arithmetic shift right. Number 2. LSL. The logical shift left. Number 3. LSR. Logical shift right. Number 4. ROR. Rotate right. And the last one. RRX. Rotate right with extend. For all instructions, RM will hold the value to be shifted, while OP2 is the shift length, or how many times the shift is performed. This illustrates how the operations are performed. For the logical shift left or LSL, the content of the register is shifted to the left. Shift how many time? The answer is depend on the value of OP2. When the content of the register is shifted to the left, the bit that is shifted out from bit 31, which is the most significant bit, will be copied to the C or carry flag in the status register, while the least significant bit, or bit 0, its will be replaced by 0. Meanwhile, for the logical shift right or LSR, the shift direction is to the right, where the bit that shifted out from the LSB will be copied to the carry flag, and logic 0 will replace the MSB that is shifted from bit 31 to bit 30. For the rotate right or ROR, the operation is similar to the logical shift right, except that, the bit that is shifted out from the LSB will be moved back to the MSB or bit 31. Note that, the bit that is shifted out, is also copied to the carry flag. For the arithmetic shift right or ASR, the operation is also similar to logical shift right, where the content of the register is shifted to the right. However, the MSB, or the sign bit is now copied or remain the same. And for the last one, the RRX. The operation is similar to ROR, except that the bit that will replace the MSB is copied from the carry flag. Now, let's look at this example, where we have logical shift left, R0, R1, immediate value 4. This means the content of R1 will be shifted to the left 4 times. Then the result will be kept in R0. Let's the initial contents of R0 and R1 are hex 0 and F, respectively. Then, after we execute the instruction, we will have hex F0 in R0. This is how the operation is performed. Where this is the initial content of R1. So, we want to do the shift 4 times. This is the content, when shift 1 time, 2nd time, 3rd time, and the last one, the 4th time. The result is F0 in hex. And the carry flags is equals to 0. The next example will be the arithmetic shift right, the ASR. Let's the instruction as ASR, R0, R1, R2. In this instruction, the content of R1 will be shifted to the right 4 time, because the OP2 now is R2, and its contained hex 4. The shift result will be stored in R0. After the instruction is executed, we will have hex FF, 050000 in R0. And this is how the operation is performed. Where this is the initial content of R1. So, we want to do the shift 4 times. This is the content, when shift 1 time, 2nd time, 3rd time, and the last one, the 4th time. The result is F 050000 and C is equals to 1. So, this is the end of this lecture, for Chapter 3 Part 2. See you again in the next video, which is Part 3, where we will learn how to use the program control instructions. For better understanding, please try to simulate all the instructions that you have learned in this chapter in Kyle Microvision. Any questions, you can message to me through Edmodo. Goodbye for now.